Okay, I've been doing some experiments from this book, The How and Why Wonder Book of Magnets and Magnetism. This is a 1963 book, but it has some interesting experiments in it. And the experiment that I'm looking at here is about induced magnetism. The idea is you pick up some paper clips, and we'll just look at it right here. It says, make a chain of paper clips. As you did when learning about induced magnetism, pull the upper paper clip away from the magnet. The chain falls away. Try to pick up one paper clip with another. It cannot be done because none of the paper clips are magnetized any longer. Okay, and then there is, in the next page up here, it does say, in both of these experiments, you may find that a small amount of magnetism does remain in the paper clips. This little bit of leftover magnetism is called residual magnetism, and it will gradually disappear with the passing of time. Okay, so it's not that the magnetism in the paper clips may go away completely. Okay, it just may be that they go away quite a bit. Okay, so I'm going to perform that experiment right over here. Okay, I might have to pause if I need to reposition the camera at all, but if I may not have to, if I can get it here. Now, I have a box of paper clips, okay? On an experiment like this, if you're dealing with something where the objects may become magnetized in the experiment itself, you can expect that when you repeat the experiment with the same paper clips, you may get a different result. Because on the first time, let's say they were not magnetized, then when you try to repeat it, you find that they are magnetized, you're going to get a different result, okay? So what I have over here is a bar magnet. It's not a very strong bar magnet, but I'm looking, I don't want to permanently magnetize these clips necessarily, and the stronger the magnet you use, the more residual there will be. So they might appear to be permanently magnetized. So what I'm going to do here is pick up two, just as it would be explained in that book, okay? Now I will take away the magnet, okay? Now the question is, you see they're still hanging, okay? And the question is, do they still have residual magnetism? Well, it certainly appears that they do, okay? Oops, hold on. Let's see. I had placed them over here, but after a short period of time, they did fall apart. I was going to hang them up, and as I was hanging them up, they separated, and now I can't lift them apart, okay? So it appears as though in this case, the magnetism did not last for that long, okay? And now, another thing that you can do is, rather than supporting the entire weight, you can see whether or not they can pull on a horizontal surface. This will require much less magnetism to pull on a horizontal surface than it would be to support the entire weight. So let's just put those, that's two that I did there. Let's try that again. Okay, because what I'll do is I'll try to, I think that went off camera there in terms of how long they might have held before they dropped it. So let's try this. This is actually the other side of the magnet. Okay, they're suspended. Now I'm going to pull the magnet away. Okay, that only lasted a couple of seconds. Okay, so this is generally in agreement with the what we saw in the book, more or less. They don't go away completely, but after a short time they might. Now another possibility is that book was written in 1963, and the material used to make paper clips at that time might have been a softer steel. And as a result, they may not have been, you might get a different result based on that alone, okay? And there might also be variability in these results. Okay, here's one where these ones actually appear to be for a longer period, okay, than the other ones. So this would be some variability. What I'm going to try to do now is I'll try to put these up on this hook. Okay. Okay. I'll have to use both hands on that. And if I manage not to knock them off, of course, it depends on how you handle it, if you handle it brusquely. So there are a lot of variables in this experiment. So these ones, you know, it does appear to retain some magnetism, okay? And we can let that sit there for a while. Now, another way to demonstrate the same thing is to use a type of steel or iron which is softer than these paper clips. These paper clips have a certain amount of springiness to them, and that has a certain hardness that may be associated with it. And it's possible that a nail could be softer magnetically and also physically. Okay, in other words, it may not retain. What we're looking for is material which can be magnetized, but it doesn't retain the magnetism. Okay, and one way to show that is using steel, the iron filings. The iron filings are pure iron. They don't retain magnetism, which is why you use them to show the magnetic field pattern. But they do attract. They will be attracted by a magnet or in a magnetic field. So if I'm taking this 3-inch iron or steel nail, I don't know exactly what the composition is. And what I'm doing is I'm attracting iron filings with it, okay? Now I am removing the magnet, okay? And what you can see is that in a relatively short time, most of the filings go away. Now, the residual here, you can see it's focused on the tip of the nail. Part of that is because the magnetic field strength is greater at the tip. And here, you can see that a little bit of tapping is enough to make the filings go away. This is a material which doesn't hold a permanent it doesn't hold permanent magnetism very long. Okay, and that is what's known as a softer magnet. Okay, I'll try the same type of thing just because we can with the one of these paper clips. Now, each time I'm doing this, I'm using a new paper clip out of that little box because I don't want a paper clip that's been previously magnetized. Okay, here I'm going to stick these into the filings to simply pull out a good amount of the and now what I'll try to do is disconnect it to see if there is an attraction to these, which possibly is more, let's say, than the iron or steel nail. Okay, this could represent harder material, not as soft in terms of being able to hold a magnetic field as the nail was. Although it does, you can see that it does go away. Okay, there's still some hanging on the end there, and if you tap it, it does go away. So there's an issue with the strength. It might be stronger than the nail. Now you can still see, though, in the background, I still have those clips, and they are still hanging on. So in that case, the magnetism was more permanent because it's been holding for several minutes. Okay, and when I asked ChatGPT for an explanation for why I might get this result, and this is with new paper clips. They were not magnetized at all before I started, and ChatGPT claimed that in 1963 paper clips were made of softer steel. Less carbon content is what normally gives you a softer steel. And that's why this experiment could have been more dramatic, let's say. We had some examples where it didn't hold it. And here's an example where it does. So there's also quite a lot of variability. Now, whether or not ChatGPT is right about this and whether a paperclip from 1963 would have been a good example. But I think nowadays a better example to show the temporary magnet looks like it's going to be an iron nail, okay? Or exactly what the composition of this nail is, I can't say for sure, you know. Steel and iron. Steel is a form of iron that has a certain amount of carbon in it, okay, and other sorts of things. So, okay, that's kind of went on for quite a while, but I just wanted to kind of show you that. And I was hoping that over time, this example might lose its magnetism, but it does not appear to be doing that, okay? So that's what we have for today. Okay, thanks, bye.